Hello and welcome to the homework review for chapter 9. These are the problems that we're going to be doing, and I'll go ahead and get started now, so try to keep this under an hour. Okay, so this is 9.2 number 1, and it's a relatively pretty simple problem. It's getting comfortable determining what your n and your x is, because your p hat, the proportion from the sample, is always x over n. So you have to be able to figure these uh, these two variables out at all times if you're reading any problems. So here they say out of 3,000 elevators, 25% of them are sticky. So x is just the number of elevators that are sticky. Okay, so to find x, all we have to do is multiply this n times whatever this percentage is. Okay. In this case, the percentage of the elevators that are sticky is 25%. So you see, I'm just doing algebra here. Okay, so that's gonna be 3,000 times 0.25, which should give me 60, 75, maybe 750. But I'll go ahead and do this on the calculator to back this up. Okay, 750. So whenever you find a percent of a number, you just multiply that number times whatever percent that is in decimal form. So okay, let's go to number 2. Okay, so we could see here, whenever you do these problems, we had started off with is it a proportion or a mean problem? Okay, and from a proportion, we either could do a one sample. This is what we've done in the past. Okay, it could be a one sample interval or a one sample hypothesis test. Okay, now mean, we've only done one sample, but there was two different things. It could have been a z or it could have been a t, and it was either an interval or a hypothesis test, or an interval or hypothesis test. Now we're going to be doing the same thing, but we're going to be adding another element here. It could be two samples. Okay, we're comparing one proportion with another proportion, and it's the same thing. It could either be an interval or it could be a hypothesis test. Okay, the interval would be the difference of the two. Okay, so whenever you're doing these problems, and you could tell that there's two samples right here, because here we have a p hat 1 and a p hat 2, and this is not sure what this p bar is, but this p value is the p value. It's the statistic we get from, I'm sorry, it's the probability that these things that would be different from each other. Okay, so we could run this whole test, but if this problem doesn't require it, we could get it from the p-value. Since the p-value is so small, we would reject the null. So this would be the null. You guys should pause and read this problem. But we're trying to see if the home team, is there a significant difference between the home team? So let's say the home team is the first one. That's the percentage of wins for the home team. We're going to assume that they're equal. Okay, now if there's an advantage, then this P1 percentage will be greater than this P2. That's what they're asking here at the end. Does there appear to be a significant difference? What do you conclude about the home field advantage? Home field advantage. So this one's tricky because it could kind of be this, or maybe a not equal to, because they don't say, but it's kind of implied that they think the home team is going to win more. Okay, but we know since it's such a small p-value, okay, there's going to be a significant difference, meaning that the home team won more, meaning that we found evidence that this p1, this is the p home, they put a home there, this would be a See, P stands for percentage or proportion. Okay. Okay, so with this alpha at 5%, okay, this is very, very significant. Sorry, they're both home. This is comparing the home team for baseball games versus hockey games. See, this P1 is the percentage of home runs from the baseball game, so this seems to be significantly higher than the hockey games. So, I'm sorry, when I set this problem up, I didn't read it. So this would be the P for baseball. We're saying this is the home game for hockey. This is the alternative, which they call H1. This would be baseball. This is hockey. I thought they were comparing home away from that. Okay, so it appears that this number was significantly bigger than this number because our p-value was so small. Okay, let's go on to number 4. Okay, this is number 4 from 9.2. Okay, so whenever you're doing these problems, you have to kind of go through this process. Do you think it's a 1 sample or a 2 sample? So right off the bat, we should be able to pick that up. And is it a percent or a mean? This is my process. Slash 1 or 2 samples. Okay, whenever they talk about like so many people out of so many people, then I know it's a percent problem, proportion problem. Okay, so they surveyed so many workers. So I'm going to go through and collect my statistics here, or my data. Showed that 137. So I have 137. So pause this thing and read this problem. So these are the workers. These are the workers. And they went ahead and then they sampled the senior level bosses, and 38 of those. Now I have an alpha of 1%. Now I'm looking for the alternative. I already know the null. Now I'm looking for an alternative to test the claim that for those saying that monitoring emails is the proportion of employees less than the proportion of, okay, so this is the proportion for the employees is less than the proportion for the bosses. So we're going to assume they're the same. You have to be comfortable doing these nulls. We're trying to find if this number is statistically smaller than this number. Okay, so this would be 2 sample proportion. So we want to open up our StatCrunch. Okay, stat. Okay, so this is proportion, 2 sample, and they would give a summary. And they're going to ask for all that stuff that I just wrote down. So you want to make sure you put the first one in, the one we think is going to be less. Okay, so it's going to be 433. Oh, I'm sorry. Out of those 433, 137 thought it was unethical. Okay, 433. Okay, and there was 38 successes out of 107. So then the null is always going to be 0 because we're assuming that they're equal to each other. If they're equal to each other, then the difference would be 0. And this is going to be a less than. I think the first one's less than the second one. Okay, 2 proportion. So I get a p-value of 22%, which means that this difference is not out of the ordinary. Okay, the observed difference that they got here was not out of the ordinary. It's not enough to say. It's not enough to say that employees were less than the bosses. There's not sufficient support that the portion is less than the portion. That's it right there. Okay, there is, so this would be this is called a fail to reject. Okay. Okay, let's go ahead and move on to the next problem, which would be number 7. Okay, so here's a confidence interval. This is a confidence interval. So it's either going to be a 1 sample proportion or a 2 sample proportion confidence interval. Okay. So what I'm interested in here is I have the first sample and the second sample. First sample and the number of successes from the first sample, and the second sample and the number of successes from the second sample. Okay. So go ahead and pause this and read this problem and then come on back. Okay, so now I have the number of men who challenged the system. 215 were upheld. Okay, women challenged it. 365 and 112 were upheld. Okay, so essentially what they're doing is they're taking, I'll just show you on this chart right here. This would be all, that'd be that distribution. And this is this distribution. And this is just one p hat. This is the p for the men. This is the p for the women. So this is the real p, but I don't know the real p. You don't know that. So we've got this p hat. So these are all a bunch of p hats. P hats for the men. P hats for the men. And this just happens to be one of them. This p hat for the men just happens to be one sample of 511. And this is just happens to be another p hat for the women. Of course, if I take another sample of these numbers, they would be different. So what I'm going to do is I'm going to subtract these two. I'm going to subtract these two. Okay, subtract these two as a decimal or percentage, and then that's going to show up on a different one. Okay, that's going to show up somewhere. I'm going to put this here in the middle, p hat men minus p hat women. So what I'm going to do is I'm going to add a little bit of this to get me to the it's 99%, so it's more than 2 standard deviations. I'm going to add an error and I'm going to subtract an error to put me over here. That's basically what it's doing. But StatCrunch is it's a lot easier. So we're going to go we're on proportions. We have 2 sample, we have summary. Okay, so we want to enter our data in here, which should be 215 and 511, and number of successes would be 112 and 365. Okay, now we're doing confidence interval. So we want 99% and calculate. Okay, so this would be the lower limit, which is to go 4 digits, so 0.03. The 0 in front of there. Okay, this is my upper. Okay, so what this is basically saying is that the men's were upheld more than the women's by the lowest level would be 3%. Okay, based on this confidence interval. Okay, 0 is not in there. Okay, because it starts at 3% and goes almost to 20%. Okay, so since zero is not in there, that means there's a significant difference. There's a significant difference that the men were more. Well, there's just a significant difference. That's all they were interested in. Because zero wasn't in there. See, if zero is in there, then we can't prove there's no statistical difference. There's no evidence of a difference. Okay, so let's go ahead and go to our next one, which would be 9. It's the last one from here. Okay, so it looks like this problem, they're kind of, they give us the ends, and we might have to find the x's. Okay, remember they're going to get a p hat from here, and they're going to get a p hat from here. Okay, so 2.1% of these, of 1669, okay, and then they gave placebos to this many people, and they had 1.1. That's 1.1%. Okay, so now we need to figure out these x's, because the computer program actually asks for x's. I guess I have to be in here. Okay, so to find the first x, I do 1669 times 0.021, which is 2.1%, and 35. So I'll go ahead and just round normally to 35. Now I want to come over, let's clear that out, and I want to find my other number of successes, which is 1657 divided by, times. Okay, and we have about 18 successes here. So it looks like there were more successes here, but you have to be careful because it's relative to how many people. Okay, so we have about the same amount of people in both groups. So these percents, this first sample percentage will be somewhat higher. So our alpha is 1%. Okay, now I'm setting up my null. So get comfortable doing these. You always assume the first P1 is equal to P2. We're assuming there's no difference. And now I'm getting my null. It says that the incidence is greater of those who use the drug. So these use the drug. So I'm testing if this P1 is greater than this P2. I'm testing an alpha of 1%, which means that if it does happen, it's pretty good evidence. It's harder to reject here. Okay, so let's go ahead and do the test. So this is a 2-sample proportion hypothesis test. Okay, proportion 2-sample. Okay, so I had 35 successes from the first group out of 1 to 6, 9. And then the second group, we had 18 successes out of 1, 6, 6, 5, 7, 1, 6, 5, 7. So there's a statistically more. Okay, and I want this to be greater than now. See, this matches up with my alternative. E left. It's back. Okay, good, and calculating. Of course, I get a p-value of 1%. Okay, I'm going to go ahead and fail to reject because it's not less than 1%. Okay, you don't see this too often where the p-value falls exactly on the alpha. So let's go ahead and see what it wants to give us. Since it's not less than that, since it's equal than that, I'll say that we did not find enough evidence. There is not sufficient evidence to support the incidence, so I'm saying there's not evidence that this one's greater than this one because we failed to reject. Okay, so it looks like, I guess since the p-value falls right on it, they want to go ahead and say that there is significant difference. Okay, so they wanted you to say, so I guess if this p-value falls exactly on your alpha, then we'll go ahead and take that as a reject. Oh, I'm sorry. That's not 1%, that's 10%. So this 1% is less than this 10%. Okay, you have to be careful with these things. This alpha is 10%. My p-value is 1%. So since my p-value 1% is less than an alpha of 10%, this would be a reject. Reject the null, so reject that. So we found evidence that this group, that this was a higher percentage as this people. I'll let you look at it one more time. See, that's 1%, and this alpha here is 10%, the significance level. Okay, let's go ahead and jump to the next homework, which would be 9.3. Let's go ahead and we are going to do 1, 2, 4, 5, 8, and 10. Okay, so this one here is a sort of tricky a little bit. I wasn't gonna do it, but I decided to do it. Okay, let's go ahead and float this so he stays up here. Okay, so what happens here is if you take this P1, I want to just understand what's going on here. So if you take the P1, we take a P2, and we subtract them. Now look at both of these are negative. Both of these are negative. Okay, so what that means is this number must have been smaller, and this number must have been larger. Okay, so this one, okay, this one minus this one, okay, and what this means is that if you take that, this P1 minus P2 could fall anywhere here. So what they did is they took a sample and they found this P hat. So the smallest this thing is expected to be is negative 12.2. Now the largest this difference is 1.6. So what happens is if you switch them and you put the P2 minus the P1, okay, this must be larger and this must be smaller, which produce positive numbers. So if both of these are negative in here and I switch them, both of these will be positive. You look, that only happens on one of them. That only happens here. So just kind of play with some numbers when you guys do that. Okay, let's jump to number 2. Now, I know that when you guys are doing these homeworks, it kind of follows this pattern where you kind of get into this section and you know what to do during that section. Be sure to make sure that you could do every single problem. So the difference, what I mean by that, make sure you could tell which different tests, because I'm not going to do it on sections. So you're going to have to be able to tell stuff like, is it a proportion or is it a mean? Okay, is it one sample or two samples? Is it 1 or 2? Is it a T or is it a Z? And even on means you have this other thing where it could be this thing called a matched pairs. It's actually section 9.4, but of this section the difference is if you take a sample from here and you take another sample from here, if they don't have anything to do with each other, okay, if they're independent samples, then we would do a 2 sample T or a 2 sample Z. I'm on these guys now. 2 sample T or Z. Now if you take a sample, okay, let's say 1 people, and you measure 2 things from the same people, then that would be what's called a matched pair. Or measure 2 things that are similar. You get 2 people that are similar within the sample. That's dependent samples. Okay, that means that your list of your first x's are related to your list of your second x's. So that's what we have to we have to kind of play with here, because they want to know if these are independent or if they're matched. The differences between IQ score tested by measuring IQ score of husbands and wives. Now I'm not going to ask you any test questions on these, but you're going to have to be able to tell which one to do in order which test to do. But I'm going to make it pretty straightforward. Okay, so IQ scores of husbands and wives, because sometimes these could be a little tricky, because if you have a husband and you have a wife, they're kind of dependent in a way, but it's kind of tricky. So pause it and kind of read over these. Okay, so if I'm looking at this second one, I know this isn't the answer, because the sampling kits of matched pairs, one samples are not related. If they were matched pairs, then they would be related. And I know this isn't right, because this is the definition of dependent. Sampling is independent because the individuals selected in one sample are used to determine the individuals. That would be dependent. So it's either A or D. And I'm going to say matched pairs, and this may be wrong, because if you pick a husband, then they're matched pairs because the wife depends on whatever husband, or the husband depends on whatever wife. But it may be D. Okay. Okay, jump to 3. Okay, so look, if we want to test effectiveness of a drug, okay, and they measure 200 men, and then they measure 200 women, 200 men before, measure 200 men, and 200 after the treatment. Now these men would be like these people, and these women over here, they don't have anything to do with each other, so they're independent. There's not a natural pairing. Okay, so that's 2. Well, we were supposed to skip that one. Oh well. Okay, so now we're going to be doing these tests. I'm on 4, and we did these already, so this is it right here. Okay, maybe a little more, because it could be a T or a Z. T or a Z, 1 or 2 sample. Should be comfortable doing 1 samples on these. Okay, effect of a treatment of respiratory infections. Okay, days of fever. Okay, so they measured 472 children, and they tested these herbal remedies, and the mean number of days before the fever went away was 0.37, so less than a day, with a standard deviation of 1.57. Now notice I'm using this S, I'm not using this sigma, because they don't tell me that this guy comes from, this 1.57 comes from this 472 from these children. So this is your sample. Okay, so the second sample, they went ahead and did 383. Okay, and they didn't give them anything. Okay, and they got better on 0.68 with a standard deviation of 1.37. And the question is was the number of days here statistically significantly less than the number of days that got better here? So the null in this case, mu, I'm going to put a treatment, is equal to placebo. And the alternative would be, let's see if they say it, claim that the herbal remedies affect the number of days with fever. Do the herbal remedies appear to be effective? So if they're effective, then that means that the treatment of herbal gets better faster, so less than the placebo group. Okay, so we could just use a 2 sample T. We could use a 2 sample T test. Okay, and find our p-value. Okay, so StatCrunch. Sorry, I have to cover this up. Stat 2 sample T, so 2 sample, and they give me summary. You should have a good understanding of kind of what's going on here, about what this test is actually going to do. Okay, if you see this pool variances, you always want to unclick that. They write something. This has to do with, did you not assume the population standard deviations are equal? Okay, it just changes the formulas up that they use to calculate this p-value and the test statistic. Okay, so let's go ahead and do this, and I want to see that this treatment, that the first one, I'm going to assume they're equal, and I'm going to see that this treatment is less than that one. Okay, let's move these out of the way. And we have this negative 3.07, 0.011, 0.001. We're testing an alpha of 10%. This is definitely less than 10%. So we found enough evidence. So we want to reject that null. Do these herbal remedies appear to be effective? Okay, they appear to be effective. This p-value is very small. Okay, so that means we're rejecting this. I don't want this to disappear, but I guess it disappeared. We had a p-value of something here. So this is definitely less than your alpha. So we reject this, which means that this is statistically smaller than this. Which must, if they did the experiment correctly, which must mean it was from the, okay, these herbal remedies. Okay, and next is going to be 5. Did we do 5 already? Okay. Looks like I had did 5 already, and before, do similar exercise. Okay, so this is a confidence interval. So it's the same type of setup. They're going to give us a sample size, a mean, a standard deviation from one group, and they're going to give us a sample size, a mean, and a standard deviation of another group. And we're going to have to find a confidence interval. Okay, so they're studying birth weight. I think I did this one in class. So for time permitting, I'm going to skip it and go to 8, which okay. You guys could do that one. It's the same thing. It's just the one we were doing before was a 2 sample t, and just do confidence interval and then put this data in. Okay, so let's go ahead and do number 8. Okay, so assume the 2 samples are independent random samples. So they're telling you, as soon as they say independent random samples, then we know that it's some sort of a 2 sample. So pause it and read it. Okay, so let's read this. Test the claim that the unsuccessful applicants are from a population with a greater mean age than the mean age of successful applicants. So let's see if this number is statistically greater than this number. So my null will never be in x bars. I know this x bar is greater than this one, but the question is are the mean of the unsuccessful applicants, we have to assume that they're equal, and the alternative is that the mean age of these are greater. Okay, so this is a 2 sample t. They give you S. This S is from these 23 people. They tell you they're normally distributed. See, I don't have 30 there. So see, this first one would be, the conditions wouldn't be met, but I have that there. Okay, so let's go right to our StatCrunch. We're doing a 2 sample Z. Okay, and let's go. The first one, 49. The mean age was 49 for the unsuccessful. Standard deviation was 7.2. the size was 23. On the second sample, the mean age was 44.4 years, and the standard deviation was 5.4 years. We had 30. Okay, we don't want to pull variances. Next. Okay, I want to know is the first age, the age from the first group, larger, greater than the age of the second group. Calculate this. Okay, this p-value here, they want us to test it as an alpha of 5%, so the 0.0072 is less than that, so we would reject. Would reject. There is sufficient age. Okay. Yes, there does. Okay. Alright, and I'm not going to do this one all the way out, but, or let's just go ahead and do it. So they're trying to test to see, okay, is the mean amount of tar and filtered cigarettes less than the median? So these are filtered. So they're asking, is the average of these filtered, the tar in these filtered, less than these? Okay. Let's see if they, okay, so here's the data here. Open in StatCrunch. So you have your data here. You know it's not a matched pair because this is a lot larger. This sample is a lot larger than this sample. Okay, so here it's a two sample T. They don't give us anything. I'm just saying if the tar in here filtered is less than unfiltered. So everything's going to be in there. Two sample. Now we have data. Okay, so you want to select these columns. So the first sample is going to be filtered. The second is going to be unfiltered. We want to unclick pooled variance. We don't want to pool the variances. Okay, we're going to go next. I think these filtered is less than these unfiltered. Is less than. I'll do the null. This is going to disappear, but I'll come back. I'll do the null. So this is the average from the filtered, unfiltered. We always assume they're equal. Now, how about the average from the filtered is less than the average for the unfiltered? Okay, so we have to find this thing. That's what we're doing here. We're assuming they're equal, so 0 is in the middle. So if this is less than this, then if I took the difference, then the difference would be a negative, because it'd be UF minus UUF, which if this is less than, then this would be small, this would be big, which yields a negative number. The question is how far is it going to go? Okay, so this is the critical value. If it falls anywhere left of this critical value, you're going to get a p-value less than alpha. Okay, which means you would reject this. We'd reject this. Okay, let's pull those data back up. Okay, less than, so I'm ready to calculate. I'm looking for this p-value. This p-value is tiny. Okay, this p-value is tiny, which tells me that yes, we want to reject the null hypothesis. It's less than. Okay, is there support the claim that the mean amount in tar and filtered is less than? Yes, we're rejecting this. We're taking this. We're taking the alternative. Yes, because the null hypothesis is rejected. Okay, that's it for 9.3. Let's go to 9.4 and we'll be done. See how we're doing on time. Okay. Just want to make sure I keep it under an hour. Okay, so there's only 4 here. We'll go ahead and do them all. Okay, so dependent samples, this is what I kind of meant when I was talking earlier about independent versus dependent, let's get this to stay up. Okay, so we have this problem here where if you take these people and you take these people and they're nothing to do with each other, then this would be a two sample T. But if you take these people and they have something to do with each other, you get data from them like pre-post or something like this. Now we have, sorry, this would be like X first, and it's one person to get two different data on the same person. Pre-post, and these would be two dependent samples. Okay, so if we have this drug that's tested on 40 males recruited from New York and 40 females recruited from California, the researchers pair 40 males and the 40 females. Now they don't have anything to do with each other. Can the methods in this section's inference dependent samples be used? No, because they're totally different from each other. They're not pairs. They're pairs from two different places. No, they're independent samples. Which that said right there, two independent samples. Now these problems here are like pre and post, pre versus post, and questions like that nature. You have one person, you put drug A here and you put drug A B and you compare the effects from the same person. Okay, that's not two independent samples. Okay, let's go to number 2. Okay, let's do a similar exercise. Now, most of these are going to be dependent samples. So what they do is they subtract this, 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 and they put that in a list, and they do a one sample on all those differences, just like we did in 9.2. Okay. So what they did is they get the BMI from, this is the same person, see this person right here. Okay. In September and April, and they're checking to see if the BMI went up, I assume. Okay, so they're not asking if one's bigger than the other one. They're just saying, hey, did the BMI change from April to September? So this is a paired t-test. It's a paired t-test because this person right here is the same person. That's the same person. This is a pre-post. Okay, so let's go and open this up in StatCrunch. Now what this does is it's not going to do it, but the calculator would get this and subtract this. See, this would be a negative number. This person gained, unless you did post minus pre. So let's just say they did post minus pre. This would be a positive number. This one would be a negative number. This would be a little bit of a positive number, positive. So most people gained BMI, but that doesn't necessarily mean that it was a statistical gain. Okay, so let's go to our T. We have a paired. Okay, we have a paired. So let's get rid of that. So let's select the column. So these are the April. Second column is the pre. Okay. See, for example, I'll just save the differences just for fun. Next, difference is 0. We always assume this is what the null, I'll pull this back up, but this is what the null would look like. It would be the U difference equals 0. And the alternative, I don't know why I'm doing that. The alternative would be the U difference is not equal to 0. It's a little different than the other one. Okay, it's a little different. Okay, not equal to 0 and calculate. Okay, so 0.20. So what happened was we did not have enough evidence to reject. We did not have enough evidence to reject. This p-value is 20%. So since the test statistic is, this is our test statistic, negative 1.52. Okay, so let me talk about what it means to not fall. So we have this 0. Okay? Here's our critical values. Here's our critical values. We didn't find them, but if it finds anywhere here, then there is no difference. Okay, anywhere into this range right here. Then we didn't find evidence of a difference. If it falls anywhere here, anywhere here, anywhere here, that means that there is enough evidence of a difference. Now what happened was we got negative 1.5, which was not far enough out there, because this gave me 0.2, which is not less than alpha. Does not fall. This is called the critical region. Critical region. Critical region. Now you can find these critical values just by using your t, and then since it's two-sided, you have to put 2 point. So if you wanted to find these critical values, you would go to your t. Okay, degree of freedom would be 4, because 1 less than 5 groups, and you'd put right here on your calculator, this would be 0.005. And the reason why is because it's two-sided. You have to cut 1% in half. Now, you've done this a long time ago, so whatever this number is, this negative 1.5 will be larger than it. We failed to reject. There is not sufficient evidence. Okay, let's go ahead and do 3. Same sort of problem, so we'll go ahead and skip this. Just do the same thing. Okay, same thing. C5. Okay, and this is sort of the same thing, but I'll go ahead and do it. So pause and listen. Okay, so they said that there's a statistical difference that these are two people that are going for an election. They're saying, hey, people who win generally are taller. So we need to find out if there's a statistical another pair because they're in the same election year. Okay, so we need to put the winner first and see if the winner is greater than, see if that difference is greater. Okay, so these are all the winners, these are all the runners up. This is a paired T. That's the winner, that's the runner up. Okay, so I want to say that the winners are greater, tall than these people. We could look at this, 17%, which is greater than alpha, but this is not enough evidence. No, not enough evidence because the null is not rejected. The null is not rejected. Okay, so that's it for section 9 homeworks. Okay, make sure you're comfortable with these. Make sure you're comfortable, and good luck.